Hello? Am I audible?
Yes.
Okay, thanks. So, by the way, my name is Vallabh and I'm a PhD scholar at IIT Madras. So, I'll be conducting this session. Mm, so, the plan is like I'll be sharing some questions and uh, I will ask you guys to attempt those, and then if you have any doubts about those, we will discuss those solutions of each of those questions, or you can ask me some questions if you have about the assignments also. So we can either start with the doubts of the assignments, or I can directly start sharing the questions. Which one would be preferred?
Think maybe we can start with questions.
Okay. So I will share a link. We are skipping the first question because I'm a bit unsure about the way I have framed it. So we'll go start with the second question for now. I think no one else is joining today. So you guys can unmute and talk really like. So the first question is about matrix conditioning, and you can attempt it. And if you have solution, you can let me know. And if not, we can discuss the solution. anyone would like to share their approach? Hello? Hello, am I audible?
Yes.
Yeah. Would anyone like to share their approach to the question shown? So the condition number was discussed in the this week's videos, right? Or should I discuss the solution?
Yes, please. I'm not sure about the approach. If
Okay.
anyone else is on the track, maybe we can wait.
Okay. Sanjay or Chandini, any of you would like to share your approach? I guess they are not on the screen. Okay. Uh, okay, we will maybe discuss the solution itself. Okay, so are you familiar with the concept of condition number, or should I revise that first?
Yeah, definitely. It was discussed in the in this week.
Mm-hmm.
Uh, what I remember from the session was it should not be high, if I remember it
Correct,
correctly.
correct. You are correct.
But
Correct.
okay.
Yeah. So what matrix conditioning essentially does is, so So this is actually a very common problem, you can say, in when you are trying to solve some problems for linear regression or so on. So let's say you have been given some data matrix. So you could have features, let's say x1, x2, x3, and so on. And so each of the rows of this, so I'm creating a matrix of all my input data. Okay. So x1 is a feature, and each row of this matrix is going to be an individual observation. So so for an example, so this could be like in a housing price prediction data set. So x1 could be, let's say, the area of the house. X2 could be some other feature like the locality or some some any other feature. So number of bedrooms, number of total rooms, uh, or some different features. So each of the columns are denoting different features, and each of the rows are denoting the for an individual house what are the values of these features. Okay, and your goal is essentially to try to predict the, let's say, the price of this each of these houses, which are, for now, for a given data set you have the prices, but you want to predict it for a new uh, new input. Okay, so matrix conditioning, what it essentially talks about is the fact that, let's say you have a data matrix. I'm calling data matrix the matrix of all these features. Okay, so I'm now going to write it like this. Okay, and this is multiplied with some weightage. So each of these are some weightage you are supposed to give to each of these features, and that is ultimately going to help you predict the price of this output. For so far, is it okay? Is the setup okay, or should I cover it again?
Yes.
Yeah, okay. So the idea is that you want to essentially find this unknown. This is your unknown part. This entire vector. You want to essentially find out the weightage that should be given to each of the features, and the correct set of weightage will help you predict for any new set of features what will be the price. That is the idea. So what happens in matrix conditioning? Oh, so the problem is typically can essentially be written as like this: ax equals b. So a is the data matrix that I have been talking about. X can be the unknown weightage. A is our data matrix, and B is your, let's say, the prediction feature, prediction variable. So now what happens is that in case when this A matrix is such that it's closer to the singularity, so maybe it could be like some of its columns are uh, so essentially maybe we should first take an example, and this was the example that I think an example was already covered in the lectures, so maybe I just uh, revise what that example was essentially talking about. So the example had some uh, four numbers over in this matrix, and there were two outputs for that, and you are essentially trying to predict the x variable here, and it was seen that for when this A matrix, when it is a well behaved matrix, which means it has a low condition number, we were seeing that the output prediction B was kind of stable. But being this A matrix being closer to the singularity makes it such that your for any small deviation in B, your prediction for X will be wildly different from what it was for a previous B. So maybe I should have some numbers here. So maybe we'll try to find some x1, x2. B1. Okay, just for sake of it. So for in this case, the matrix, this A matrix, is not actually close to singularity. So you can actually find the determinant of this thing, and it will not be very close to 0, and it will end up being such that now if you try to find an x1 x2, you will get some answer of x1 x2. But what happens is that when this A matrix, the data matrix, is such that its determinant is closer to singularity, let's say we pick some numbers to make it close to singularity, let's say maybe 2.0001 to some, here if it's 3 then it has to be, I don't want to make it okay, maybe let's so I can put here 6. This is okay, yeah, fine, either way we are close to singularity in either case. So this matrix will now, if I try to find x1 x2 solution for some b, for a specific b I will get some solution of x1 x2, but if I slightly change b in some decimal places of any of the values, I will get a wildly different x1 x2, and that is the problem which is very common in fact of important consideration when you are trying to solve some linear regression problems. And in fact I actually experienced this problem during my own research topic. So we will come back to the question that we were looking at. Yeah. So in this question you have been given some 4 matrices, and you can it's actually just by visually you can see what their determinants would end up being. The options are purposely made to look like that the point is that that 0 point, like decimal and small deviation, that is not the real problem. The problem is it being the determinant being closer to 0. And so can anyone now, the concept being told, can anyone guess what the correct answer should be? So essentially an ill condition matrix is a matrix with a high condition number, and that matrix is likely to be something which is whose determinant is closer to 0. It did not necessarily be, but it could be.
Okay, so option B.
Yeah, exactly. Yeah, so that's the answer. Anyone has any doubts in this point, till this point? Okay, so I'm assuming no one has any doubts, so we can move on to the next question. Okay. Yeah. This is actually a very simple question, but some points I just wanted to. So what all can be estimated from a gradient field is what we want to look at here. So we are looking at question 3. true, I think. Okay, we have two different answers. So one answer is that D. So minus 6 could be a stationary point of the function. Okay, and can you give some reason why you think so? I mean, why do you think this statement is definitely not true? The other option we have is C. 0 0 local minima. There is direction in the figure, so gradient is non-zero at 6x. Okay. Oh yeah, minus 6, minus 6. About the option C, uh, can you give me the reason why you think that is not the correct? Oh, C equal to true, you want to say? Yeah, I mean, we want to find out which is not true. I mean, for sure not true. I think B. Okay, so we have okay, we have can you give a reason why you think B is not the correct answer? B is the correct answer for this question. Feel free to unmute yourself and discuss. I mean, this is a short meet only, hardly 10 people. Uh, okay, so the thing is that B is the option that is for sure the statement is not true, because as you can see the gradient field is going away from the 0 comma 0 point, and it's all pointing away. That means that point can't be a local maxima. The gradient field essentially tells in which direction the function is increasing the maximum. It has the steepest increase. Okay, so B is the option that you can for sure say that it's not true. In fact, B is the local minima of this. Is global minima of this function, the way I plotted it.
How should we think about this 6 6 and minus 6, if at all those are stationary points or not?
Yeah, so actually the options were kind of trick options. I mean, they were just to distract you guys. The thing is, 6 and minus 6 comma minus 6. If you look the way I had actually plotted that function, you can see that all the gradients are pointing. I mean, the pointing towards those points, and then so they are kind of the local maxima at that point. And but you can see that the arrows are still moving away from them also, towards, I mean, beyond 6 6 and minus 6 minus 6. You can see that the arrows are still moving away from them. Is that making sense?
Yeah, okay, thank you.
Yeah. How do we know that it's local maxima or minima at B? At B. You mean the 0 comma 0? Yeah. So the thing is that this is a gradient field. The definition of a gradient field is essentially that all the arrows are showing in which direction the function is increasing the maximum at that point. Okay. So if you take any arrow in this entire figure, so any of those small arrows, maybe I will switch to the notes thing. So if you take any arrow in the figure at any point, at that particular point, let's say this point you chose on the figure, the arrow is actually telling you in which direction the function is increasing the fastest. Okay, so as you can see, for the origin here, all the points are increasing. So in fact, closer to origin, the gradient is very low. That's why the arrow's lengths are smaller. But as you go away from the origin, the arrow lengths are increasing, which means the closer to origin, the slope is low. It's not increasing very rapidly in any of the directions. But all the arrows that are present in the figure, they are all pointing away from the origin, which means in any direction you move from origin, you are having an increase of the function. Is that making sense? Okay, understood. Yeah. So how is it global minimum? I think that part is answered. Someone asked, how is it global minimum? Hira Ballab. Is it answered? Or do I need to clarify anything else? Okay, yeah. So that's the whole point of the question. Okay. Maybe first read through this part, and because I can't show the entire question in the so maybe first read through the description of this question, then we will go to the options for this question. Okay, so the question is saying that the in machine learning practices, Taylor series expansions are very often used, and we use them whenever we want to try to approximate some nonlinear functions. And so the thing is that Taylor series approximation, they are always valid about a particular point. And this question is kind of trying to give some idea of what happens when you use a Taylor series expansion. Has everyone read the description for the question 4? Shall we move on to the options?
Yes, read.
Okay. Can I get a more response so that I know that everyone has read and we can move? Okay. Okay. So I'm getting responses. So I'm assuming that everyone has read this description, and we are moving to the main question here. So the given data points were these data points, y and x. They kind of look like a sine wave, and we want to try to approximate those with a polynomial function. And the point is, yeah, we will discuss. So which of the following options do you think will be the best suited option for approximation? A, since it feels like fitting a line there. will be accurate enough. So we have one answer which is a first order polynomial about x equal to 0. How many points are given? Okay. This is the graph that we are looking at. So I think, I don't know, 10 points maybe. We'll wait for a few minutes and then we'll discuss the solution. Till then, you are free to suggest your solutions as well. I mean, if you have answer to the question, you feel free to unmute yourself and let us know. Option A seems to be correct. Okay. So by the way, D is correct, I think. Okay. So just to clarify, we are here looking at a regression problem, not a classification problem. Okay. So people who are saying option A, we have an answer for D also. So a 10th order polynomial. So would anyone like to share their intuition why they think option A or option D is the correct answer? So the question is that we want to fit a curve through these points, data points, and find a function y is equal to f of x, which we want to be a decently lower order polynomial, and we are planning to use Taylor series expansion to do it. But the thing is that Taylor series expansions are often carried out about a nominal point, and in this case we have chosen that nominal point to be 0. That's why all of the options are saying about x equal to 0. and we want to consider which order polynomial would be a decent fit for this kind of function or this kind of data. In that case, 3 degree can work to accommodate the two critical points. Okay, yeah. So is everyone on the same page? Can I, or should I explain? Okay, I will. So the answer is a third degree polynomial, and maybe I will explain that a little bit in detail. So please explain. Yeah, I'll explain. So the thing is that when you try to fit let's say a linear curve, uh, so what a Taylor series expansion is essentially going to end up giving you is so you are trying to find a function y is equal to f of x. Okay, so this f of x is now, so what this is going to tell is for any other x, what should be my predicted y is what this y is equal to f of x function will allow you to do. Now when you say I will take this f of x to be a linear polynomial, which would mean that there is some, so it will be some c1 times x plus c2, let's say. So this is what you are allowing it to be. And now if you want to look at this data and you try to think of trying to fit a line through this data, so even in a best case, the best fit line would look something like that, which will try to minimize all the distances like that. But we can do better. Like we can try to fit a quadratic through this, and maybe it might look but a quadratic is a problem here because it might, let's say, fit something like that. So it covered a lot of points, but it might end up missing these points here. But as opposed to that, if you think of a cubic fit, it could end up giving you something like that. So it did fit the points that we had in front of us decently well, but it's not guaranteed that the function was actually like this beyond this point. So beyond this point, if you look at it, the function need not actually be the way the cubic is making us think that the function should be. But that is the catch for using Taylor series approximations. You are always going to be accurate around this point. So in this case, the around about 0 point, that is valid up to, let's say, this range only. So only for x within this this interval, we are saying that our Taylor series expansion might be valid. Okay. Is that explanation okay, or should I repeat some part or explain it differently? For simplicity argument, line could be fine as well if the difference in attributed is attributed to some noise. What do you think? Okay, since we are in a bounded domain with finite points here, won't it lead to overfitting? Exactly. So the thing is, for now here we are assuming that these were our data points. Like there was no, we were actually trying to fit the best way we can to this set of data points, and one of the options was about a 10th degree polynomial, and that would definitely lead to an overfit curve. So a 10th order polynomial might fit perfectly through this, all of these points, but it might be something like, okay, I made it okay, you get the point. So it would fit perfectly through each of these points, but it need not necessarily be the correct way of getting the intermediate predictions. Yeah. So 10th order polynomial might fit it perfectly like this. The point that I actually wanted to convey was that using Taylor series expansions, you can approximate functions, but you'll be valid up to a range from the original point only. By the way, where these questions are loaded, are they available? Okay, yeah. For people who joined later, I'll share this link again.
Yeah, sorry. Yeah, in general, I got the same question because the previous one also I was missed. I didn't know like where to look for this.
Yeah.
So are these are extra available than our weekly assignments, right?
Yeah. These are addition to weekly assignments, just to maybe give a different perspective of some of the concepts. Or also, these sessions
Mhm.
is actually like you can ask me some doubts if you have about the content of the week that was covered in that week.
Oh, okay, okay. Thank
Yeah.
you so much. Yeah, got it.
Can you explain in critical point view manner? What do you want to be explaining? Okay, critical point. Okay. So the idea would be like, so if you have a cubic function would have zeros at, let's say, at this point, and somewhere else also. So having three critical points for a function that you are using for approximation would ensure that you will come back like that. So if you had only two critical points, which means you are using only a quadratic, then you might have this, and there is no way you are coming back to below. That's the whole idea. And if you are having a line that is just one critical point, and you'll not have this kind of uh, waves in the data. Okay, yeah. So we will move on to the next question. Yeah. So we'll now be looking at the fifth question. Okay, we are getting answers here. Option B and saddle point. Okay, so we have two different options. So, anyone else would like to, is there anyone else still trying the question, or shall we discuss the solution? At the end of the class, could you discuss a little bit on quadratic form matrix and its derivative and its relation to SVD, if there is any? Okay. We'll have to compute partial values and also Hessian to get some answer. Don't know how to do. Okay. Okay, so shall I discuss the solution then? If I, or is anyone still trying? Guess is a wild guess. Okay. Yeah, your guess is quite on the mark. Okay, so I'm assuming that everyone has tried, and we will just discuss the solution here now. So you have been given this function z equals to sin x plus cos y. We have been asked something about the point xy is equal to 3 pi by 2 comma 0. When will the record video link uploaded? Yeah, the recording will be uploaded today itself, and in the announcements they have shared the link from where you can access the recordings. So this z function, so if we want to calculate the partial derivatives of this function with respect to x and y, so we will have some dz by dx and a dz by dy for any random x and y. So if we derive this with respect to we have been told that x and y are independent, so we don't have any derivative of y with respect to x term. Okay, and then what we are trying to do is we are trying to find this quantity or this quantity. And in this case, as you can see, the derivative of this part, let's say d del z by del y, is only a function of y. So if you try to find the derivative of that with respect to x, you are ultimately going to get 0. And similarly for del z by del x is a function of x alone, and if you try to find its derivative with respect to y, you will end up getting 0. Okay. So when you are trying to calculate the Hessian of this thing, you only have to consider the diagonal terms. I mean, only the diagonal terms survive here. So we are writing the Hessian of this, and as we saw here, the diagonal terms end up being 0. And you have this thing as the Hessian. And you ultimately get now a thing to notice here is that since this is only a diagonal matrix, that means all the terms along the diagonal, they themselves are going to be your eigenvalues. Okay, so what is going to happen is that for any particular chosen xy, let's say here the 3 pi by 2 comma 0, so did I make any mistake here? No, that is correct. Yeah. So as you can see here that the diagonal terms will end up at substituting 3 pi by 2 and 0, you will end up getting minus 1 and 1. And this is if this is your Hessian matrix, it's neither a positive definite nor a positive negative definite, so it's kind of in between, and that's why we can classify this thing as a saddle point instead of this being a either of local minima or a local maxima. This is something in between, so it's a saddle point. Is this okay for everyone? Do I need to go over some part? Please feel free to what exactly saddle point means. Okay, so in, let's say, we'll first look at a 2D example. So in a 2D case, this kind of thing we would call a local minima. This kind of thing we would call a local maxima, and something in between, which is neither a local minima nor a local maxima, let's say something like that. This point now is, it's a, from one side you are feeling like you are climbing up the slope, but from the other side you are saying feeling like you are moving down the slope, and it's neither a maximum nor a minima, so it's a saddle point. That's all. And in 3D this kind of looks quite like a saddle, so the horse saddle. So I'll have to try my best to draw this. So in a 3D space, the function is in, maybe we should change the color. So the dotted part is away from you and the dark part is towards you. And so if you are looking at this function from front, you are seeing that it is rising along this axis from this point. So in the horizontal, maybe we'll name the axis here, let's say x and y. So along x you are seeing that the function is increasing here, increasing in that direction, but along y, if you try to see it from this view, so if you are looking at the function from here, you would end up seeing the exact same kind of picture, but instead it will be flipped. So your y-axis will be along this, and you are seeing from here. So so is this part making sense? So you need to kind of imagine a 3D figure here. Okay, I hope. Yeah, okay, I guess it was clear. Anyone else has any doubts for this point? Nice explanation. Okay, thanks. So we will move on to, oops. Yeah, so question 6 and 7 are going to have the same setup, so we'll focus on the question 6 for now. zxy and zyx in all cases or certain cases. I don't know what you are saying. Are you saying that the whether the Hessian will always be zxy is, I mean, partial derivative of, yeah. Actually, it need not be the case, I think. Let me take some example and see. I mean, you can kind of cook up some function such that okay, till then we'll see the question 6 and 7. I will try to think of some function for which we don't have that case. Okay, we have one answer, -4. Would anyone else want to share their answer? -3. Okay. Okay, actually class 11 method is all we are expecting here. Is anyone else still trying, or shall we discuss the solution? Okay, we'll discuss the solution now. So you have been given this function 2x plus y, and you want to minimize that by changing different values of x and y, and then you have been given some constraints: x square plus y square less than equal to 2, and we've been also told that x is between -1 and 1. So the first thing actually we can try to do here is that we would like to see how the different contours of this 2x plus y would look like. So if you wanted to plot the line 2x plus y equal to 0, so how would that line look like? So it's a line which is y equal to -2x, right? So maybe something like that. So I'm drawing x here, y here. So it's a line which is having a negative slope, and it's not exactly cutting this thing along y equal to x. It's a bit sharper slope. Okay. Now, if you had a line, so this is all the points for which 2x plus y, this function's value, is equal to 0. Okay. But now if you wanted to look at all the points for which 2x plus y is, let's say, equal to 1, then you would have that line somewhere here. Where this point, so maybe this point is going to be 0 comma 1, and this will be half comma 0. Okay, and so on. You can keep on drawing different lines. So I can draw any 2x plus y equal to some constant c, which is, let's say, for now a positive number. That line would be somewhere here, and you can similarly draw any line 2x plus y equal to minus c, or where c is still a positive number. So those lines would go somewhere like that. Okay, and the thing is that this line is now having the value 0, but this line, let's say, has a value 1, and so on. It is keeping on increasing towards this direction. So as you go along this direction, the function value, the value of this 2x plus y, is going to keep on increasing. Whereas if you go in this direction, the value of 2x plus y is going to keep on decreasing. Am I making sense here? So these lines that I've drawn here, don't imagine them to be in this same xy plane. Instead, let's say if you had a x, y and z axis, the 2x plus y equal to 0 line was something like that, which was in the plane, and the other lines which are going in that direction are all above this plane, and they are keeping on going away and away. So, and they are at heights, different heights. Okay, and if you go in the opposite direction, you will see these lines keeping on going below the y equal to x plane. So I just, okay, this has already become very messy. But you get the idea, right? So this x equal to y plane, if you now had this line 2x plus y equal to 0, this line was on this plane, but all the other are having this function value above. So if you went to the right, you are having a function value above, and if you went to left, you are having function value below. So, and our goal is now to find the minimum of this function. So we know that we want to move towards left, basically. Okay. So now I'm going back to the 2D plane. I think I should zoom a bit. And on this, let's draw the constraints that we have. So the first constraint was x square plus y square equal to 2, or less than equal to 2, which we can essentially say everything that is there inside this circle. So that was the constraint, right? Yeah, x square plus y square less than equal to 2. So this is a circle with radius root 2. And we also have a constraint of x not being, the magnitude of x not being greater than 1. So we are restricted to this domain only. Okay, so far so good. Anyone has any doubts till this point? Okay, so now as we saw in this scenario, so to get, so our function value that we are actually interested in is this 2x plus y value. If you keep on drawing lines of different magnitude of this 2x plus y in this direction, what you can see here is that this point here is what we are hitting. The farthest you can actually go from this in this direction is actually this point, which still keeps you within the domain. I'm trying to give some more intuitive way of solving it for now. In the next few weeks, when SVR and support vector machines and stuff will be discussed, you will have these Lagrange multipliers and those concepts also introduced. So maybe we'll look at those approaches at a later point. But for now, is this intuitive way making sense to everyone? So now we are interested in what this point really is, right? So this point is actually when x is equal to -1, and this entire line is x equal to -1 actually. So the point at which this will intersect the x square plus y square equal to 1 is this y equal to 1 also, and that essentially gives you the 2x plus y answer. Oh, y equal to -1, sorry. Okay, so if you substitute, you are going to get -3 as the answer. Okay, so any doubts at this point? No. Okay, thank you. So now we can move on to the next question. Now this is actually a very simple question, seeing the explanation. So for the previous optimization problem, we have been asked which of these is true statement. anyone would like to give the answer? A, exactly, yeah. So the reason this question is given now, as a homework, maybe you guys can look at what if instead of the constraint that was given here as x equal to -1 to 1, if you had y being restricted in -1 to 1, what would the answer be? Okay, so you can look at and basically try to find the answer for the first question, the sixth one, and also the seventh one. And the answer is not among these options, but you can try to find that answer later. And interestingly, the option for that case, you will see that option C would be the correct thing, when the constraint would be on y being between -1 to 1 instead of x being in -1 to 1. By the way, I'm talking about, when I'm saying constraint, unconstrained, I'm only talking about this constraint, the x constraint, not the x square plus y square constraint is still present. Okay, the extra constraint we are talking about is only this x equal to -1 to 1 and y equal to -1 to 1 for seventh question. But yeah, you can look at it as homework. Now we will look at eighth question. So anyone has solution to question 8? Would anyone like to share their approach? Okay, we have one answer B, and that is the correct answer. Anyone still attempting, or shall we discuss the solution? We can discuss, please. Okay, thank you. Yeah, I mean, if you have any doubts, please let me know soon. Like, yeah, we can discuss. So, so here we have been given a vector valued function. So in general, whenever you whatever we looked at so far, we were only looking at scalar valued function, which means I give you an input xy, let's say. My output was only one number. It is in the previous examples that we talked so far. The output was always a single number. But here we are having a vector valued function, which means the output itself is a vector. The function, so in goes two numbers, x and y, out come two numbers, uv, like that. So the vector valued function that we are having is u comma v is equal to x square plus y and x plus cos y. Am I writing it correctly? X square plus y and x plus cos y. Yes. Okay. So in fact you can have a class something like scalar. So basically you have two types, let's say, consider scalar valued and vector valued functions. And for scalar valued function you could have a single input, in which case it's a single variate function, and for a scalar value function you could have multiple inputs, so univariate or multivariate. And similarly for vector valued function also you could have a single input, so a single number goes in, let's say x, but the output is still a vector, and that function like that could also exist. So that would be a univariate vector output function. And you could also have multivariate multi output function. So all such things can exist. So in this case we have two inputs, x and y, for our function, and the output is also two numbers which are u and v. And so in this case this is our u, this is our v. Okay, so u is x square plus y and v is x plus cos y. And you have been told that for this vector valued function there is a point x naught comma y naught where the direction of steepest increase for both u and v is the same. So the direction of steepest increase for u would be given by del u by del x comma del u by del y. So this is a direction, right? And the direction for so the direction that we are talking about is actually in the xy plane. So you are interested in what should I do to x and what should I do to y, so that I will get u in u increase in the maximum which direction should I, what should I do to x and y so that I can get u value to increase the maximum. That is what the steepest direction for u and v basically means. So del u by del x and del u by del y is actually a direction, and if for any given point if you calculate this vector, you are going to end up having that direction in which u is increasing the fastest. And similarly you can actually also calculate del v by del x and del v by del y. That is also a vector, and that will give you a direction in which v is also increasing the fastest. So for this function, in this question we have been told that there is some x naught y naught where the direction in which you have to move to get the fastest increase in u and the fastest increase in v is actually the same direction for this question. So if you calculate del u by del x is supposed to be 2x and del u by del y is supposed to be 1. Similarly here del v by del x is 1 and del v by del y is minus sin y. Okay, so now if both of these are actually the same direction, then 2x has to be equal to 1 and minus sin y has to be equal to 1. Minus sin y is equal to 1. So this will give you x is equal to 1 by 2. Y can be, it's actually infinite possible y's, but there will be some y which let's say you can have pi by 2 minus pi by 2 rather. You could have this thing, or you could have 3 pi by 2 and so on. So any of those would valid, but you are supposed to pick one from the set of options. So yeah, here. So B option is actually the one which is also one of the possible cases. Is that making sense, or should I revise any of the part? Alright, okay. So I think we can move to the 9th question then. The 9th and 10th question are just kind of conceptual, they are not specifically numericals. Yeah, D answer, yeah. So yeah, basically you will also see this in the next week's videos. So I guess I don't need to explain, both of you got the answer correctly. So maybe we'll move on to the 10th question, or does anyone want me to cover? No, okay. So we'll move on to the next question. So the 10th question is also kind of conceptually. Okay, here it's separated into 2 pages. So we'll first look at the description here, and once all of you have read the description, we'll move to the options. So have all of you read the description? Shall we move to the options of the question? Okay. So maybe I will still keep the equation over here. Yeah. This thing is. We have got one answer. Is anyone else still trying? Or shall we discuss? A won't be right choice, I understand, but cannot eliminate between B and C. Okay. Actually, for this question, I can share a script. Okay. So maybe I will discuss the theory first, and then I will share a script, and I will also upload it to that same folder. Then maybe you guys can also take a look at it. So the so this is now a modified expression for our usual gradient descent update rule. So what you are seeing here is that there is a additional term beta times xt minus 1. So it's called a momentum term for a reason. Okay, so when we did this part was only telling us that we should move in the direction. So since we wanted to reach a global minima, we are trying to move in the direction in which the gradient is, we are trying to move in the opposite direction of the gradient basically, and we are just trying to scale that with a value alpha. Instead of moving the entirety of the distance, we are trying to scale it so that we don't diverge, as we saw in the previous question. So this term, this beta term, is actually called a momentum term. And so what this essentially is trying to do is that we should keep on moving in the direction in which xt, the x direction was already moving. So it's actually a trick to escape a local minima. So maybe I will draw some. So what this term is actually doing is that, let's say your the vanilla gradient descent for some alpha value, you might end up going down, and you might get stuck here. Let's say this was a, I didn't draw it well, but let's say it was a local minima like this, and then your regular gradient descent ended up settling at this point. Okay, now what this beta term is actually doing is, beta term is saying we should keep on moving ahead in the same direction we have been keeping on moving. So if we were decreasing, so if we are moving in this direction, we should keep on carrying, we should basically carry that momentum towards in the movement of that direction, and we should move ahead and end up at this point. That is a intuitive idea of what this term is actually doing. Okay, so this is telling that the previous xt minus 1, look at that what it was, current xt what we got. So we are basically checking the factor of what is going on, what has been happening before, and do that same thing because we are adding it. So beta is actually positive here. Okay, so we are adding it to the thing, so we are actually ensuring that we should keep on carrying the momentum of what we have been doing till now. Okay, is that making sense? Yeah, so maybe I will share my screen from my laptop. Does it always work? It always find a global minima, and does it always converge? Could you guide some resources where to understand it? Yeah, I mean, even this doesn't guarantee that you will always converge to a global minima, but I will share you a script, and maybe you can you can read up some online resources about it. I don't know right now any specific resources, but I'll see and send you on maybe next time if you are present. I will try to share that resources. So this is an implementation of that same algorithm, and you can see that here beta into xi minus. Is my code screen visible here?
Yes.
Okay, thanks. So yeah, so I've just written the updated gradient descent rule, which is having this beta term also, and I will share this script also with you guys, and you can take a look later. So yeah, this is what is actually happening for a particular value of beta which we have chosen as 0.7. If we actually choose it 0.4, and I'll just close this. Yeah, you can see that if the beta value, the momentum itself, is not sufficient, you can still end up converging to that local minima. Okay, and it will kind of behave like a regular gradient descent only. But if that term was sufficient enough when we did 0.7, you saw that the momentum was enough to get carried down, and you were able to get to the global minima of the function. Okay, and then we can also highlight a disadvantage of choosing a very high beta. In fact, I will go much ahead and put 0.99. Yeah, and you can see here that it's actually the momentum is so huge that you are keeping on moving in the direction in which you are moving, and you will ultimately end up oscillating here back and forth. Okay, so that's it. So I will share this script with on the same in the same folder, and you guys can take a look. Yeah. So I think we are almost at the end. Uh, would you guys like to give some feedback how the session went? Some improvement tips. Could you please share the PPT? I'm not sure. We didn't. I didn't share any PPT today. I just shared this drive folder. I will put the link again here. Oh, okay, okay. Maybe I will upload the. I will put the link of this drive in the description of that YouTube video that I will upload, and you can check from that also. Clarify many concepts. Okay, thanks. Okay. And is this format okay for everyone? Like some questions, then their discussion of their answers, and so on. Okay. Okay. So we'll keep following this format, and every Monday I will be conducting, and there will also be sessions on Saturday, and there is one on Tuesday also. As you must be getting notified from the NPTEL. So yeah, so we'll wrap up today's session, and thank you for attending. I hope it was helpful. Yeah, sure.